This begins E555 with Dr. Zahid. It's January 30th, 2014.
Thank you very much. Good morning, everybody, and welcome to E555 again. Let's continue our discussion from last time. So far, we have been talking about single queues. Single queues means what? Means just one router, one server, one buffer. Clear? Right now, we need to look at the wider picture, which is what is known as multiple queues, or what we refer to as network of queues. Network of queues. Okay, let's start first of all with a simple case, which is what is known as feed forward networks. Feed forward networks, what does it mean? Packets are not allowed to be a queue more than what? Once. What does that mean? When a packet arrives to a router, for example, and the router will what? Will send it to another router, that packet is not going to come back to the same what? To the same router. It will only move forward. It's not going to come back. Clear? Okay. Let's take first of all a very simple example, which is tandem queues. Let's look at this scenario. I have a queue here, or the router. The outgoing packets will join another queue. And this is a what? This is the router. We call this a queue. Tandem means what? In serial. One after the other. Clear? One after the other. Okay, let's understand what I'm talking about. Let's assume that the service time in here is with parameter of what? Mu1. This one is exponential with parameter what? Mu2. This is what? Poisson with an average. With parameter, average arrival rate is what? Clear so far? Okay. Notice, by the way, I did not say any the arrivals to this one, because the arrivals to this one are what? The departure of this one. Did you get my point? To this one are the departure of this one. We need to understand what does the departure process look like. Okay. Concentrate right now. Single server case. So we have a single server here, a single server here. Okay. A what? An M1 queue. Do we agree? Do we agree? The first queue. Why? Because the arrivals, these are external arrivals. Because the arrival process is what? Positive process is what? Exponential. Clear? Notice, by the way, I cannot say the same thing about the second one. And prove, unless I can prove that the arrival process to the second queue, which is what? The departure process at what? Of Q1 is also what? A reformer, if I can prove that, then it means what? It means I can treat this one also as a what? As an M1. Clear? We will see. Let the state system be N and N1 and what? N2. N1 and N1, which where N1 is the what? Is the number of what? Of packets in Q in system 1. Both what? Both waiting and being served. Can you zoom back, please, a little bit? Thank you. Okay, let's say it's hitting it. NI, system what? I. So what is N1? What is N1? N packets, the number of packets in this system, both waiting and being what? Served. N2 is both waiting and being what? Served in here. Clear? And I'm interested in finding the joint PMF, the joint PMF, which is what? What is the probability that N1 equal to N, N2 equal to what? M. So instead, previously when we were talking about, we were only interested in finding what? The probability of N equal to N. Clear? Which is what? Which is the P packets in the system, both waiting and being served. Right now we are interested in finding what? Why? Because we do have what? We do have two queues. Clear? What did we do in a single queue case? The what? The state transition diagram. Clear? Can we set up the state transition diagram here? The transition diagram here will be two-dimensional rather than what? Let's see if you can help me. Let's look. Consider the following. State transition diagram. Let's see if you can help me. 0, 1, 0, 2, 0. This axis is what? Is N. 0, 0, 2. This axis is what? M. 1, 1, 1, 2, and so. I messed up? Did I mess up? This is 1, 2. No, I messed up. I messed up. This one should be what? 2, 1. I'm sorry. This one should be 2, 1. This one is 1, 2. This one is what? 2, 2. And so on and so forth. So on and so forth. Tell me, what does this 0, 0 mean? This 0, 0 means what? There are no packets in system 1. There is no packet in what? System 2. Can you tell me what is this 2, 0 means? 2, 0 means what? There is what? 2 packets in what? In system 1. One of them being served. One of them is what? Waiting. Empty. Why? Because this one has not finished service yet. Did you get my point or not? Did you get my point? Good. Say, by the way, what does the 0, 1 mean? What does the 0, 1 mean? This queue is what? And one packet in here being what? Served. What does 0, 2 means? This one is empty. There are 2 packets in the system. One being served and one is what? Waiting. Clear? Okay. Let's see if you can. Can I go from 0 to 0 to 1, 0? Under what process? An arrival process. An arrival process came. This one will result in, goes to what? This. Do you agree? Agree? Okay. How about the same? How about this one? Is it the same? This one is the same. Clear so far? Clear so far? Oh, how about from here to here? Can I go? Can I go from here? By the way, can I go from here to here? I cannot go from here to here. Can I go from here to here? What happened? It's, which is what? Which is in the system, in the second system, Under what process? Server process. What is this? Mute. Clear so far? Clear so far? Okay. How can I go from here to here? Under what? Arrival process. Let's see if you can help me. From here to here. Go from here to here. Under what? Under mu1. In other words, the first server finished service. Yes? And that packet goes right now where? To the second one. So mu1. Clear? Can I go from here to here? First of all, can I go from here to here? Here to here. Can I go from here to here? Under what? Under mu2. Clear? So this one is what? Clear so far? Are the rest exactly the same? Are the rest, in other words, this one exactly the same as this one? In other words, the pattern will what? Will repeat itself. Do you agree? Pattern will repeat itself. So for example, from 0 to 2, sorry, 02 to 01, what do I have? I have an arrow. Let's write it down so that you can see. What is this? mu2. What is this? And what is this? mu1. What is this? mu2. Do you agree? Does it repeat itself? And it repeats itself. Okay, now let's write the transition equations. The state, steady state, transition, state, transition, equation. I'm not going to solve it. I'm going just to write it. I'll let you solve that at home, but I will show you an interesting resulting. Let's help me. How many different nodes do I need to take? How many different nodes? A node, yes. I need to take any node in this what? In this row. Yes. I need to take any node in this column. And then I need to take any what? Any node within the, I mean, in any other than the what? Other than this row and this what? Column. Anyway, help me. Let's take this one, the edge one. What do I have? Lambda P 0, yes, equal to what? mu2 P 1. This equation 1. Yes or no? Okay. Now, let's see if we can help. Take any node in here. Any node. Repetition. Any node. How do I write it? First of all, what is the outgoing? Any node here. Pick any one. It's what? Lambda and what? mu1. How I write it? Lambda plus what? mu1 times what? Be careful. Times n 0. Are you following me on that? For anyone, n equal to what? 1, 2, 3, 4, 5, any one of these. Yes or no? You don't try to write it because it's repeating, the pattern is repeating itself. Clear? Tell me, what is it equal to? The what? Outgoing. Where are the incomings? The incomings are what? Here. Yes? Lambda times what? Let's see if you can tell me. This one is coming from, so it's what? P minus 1, 0. Do we agree? Do we agree? You are losing me? What is the other one? Let's see if you can tell me. Where is the other? It's what? From up. Yes? But it's the same what? It's the same value of what? N. Do you agree? So what is it? Plus mu2 E what? N. Yes? And what? You lost me here. Pick any one of these. Pick this one. Yes? Where is it coming from? The N is the same as what? Is now 1. Yes? 1. Clear? What is it? Pick anyone here. Pick anyone here. What will it be? P. Where are the outgoing arrows? 1? and this one. Yes? So what do I have? Let me write here for n equal to what? Clear? And give it to me here. What is it? What is it? Anyone. Pick anyone in here. What is changing in here? What is changing? Yes? Pick anyone. So what is it? Lambda plus what? U2 times what? P 0 M. Do you agree? Agree? What is it equal to? These are the out, lambda and mu2. Now what is the incoming? What? From here and from what? Here. Yes? Let's look at this one. This one is coming from mu2, yes, times what? P0 M plus 1. Do we agree? Agree. What? It's the same column, which is the zeroth column, yes? But it's coming from what? From the... What is this? Can you tell me what is this now? Remember, from any one of these, plus lambda, yes? No response. 1. Huh, I messed up? Oh, mu1. I'm sorry. mu1. Okay. P what? Concentrate. Let's pick this one. Yes? Where is this one is coming from? This one is coming from what? The 0 becomes a what? A 1. Yes? But it's coming from lower. Which is what? What do I write here? M minus 1. Can you zoom in, please, a little bit? Just a little bit. Thank you. Thank you. Did you understand where this came from? Yes or no? Okay. This equation what? Equation. The M is what? One more equation. What is the one more equation? One more. Any node in the middle. Yes? What do you... Let's finish this one so that you can see. Yes. Pick any node in the middle. Yes? Outgoing. How many outgoing? Pick any node in the middle. And pick this one. 3, which is what? This and this one and this one. Yes? So what do I say? Lambda, what? mu1 plus mu2 times what? P, comma what? M. Are you following me on that? Where n, remember, n is what? 1, 2, 3, 4, so, and the m is what? 1, 2, 3, 4, so. So pick any node in the middle. How many outgoings? How many? No, this one is outgoing. How many incoming? Sorry, how many incoming? There is one in here, and there is one in here. Yes? Let's begin incoming. What is it? It's lambda. Help me. It's coming from this side. Yes? So it's what? It's the... Is it the same? Is it the same? Is it the same M? Is it the same? Is it the same M? It is the same M. But the N is what? The previous, right? N minus 1, comma what? M. This. Yes or no? Okay. In plus. Let's take now this one. Where is this one is coming? From the same what? Same N, but the M is what? Plus what? So what do I have? Plus mu2 times what? P, N, M, plus 1. And finally, where is the other one? Where is the other one? The other one is coming from here, which is level below, and what? One column to the right. Yes? So what is it? It's mu P of what? N plus 1. And very good. Did you get why is this N plus 1 and M minus 1? It's coming from what? This, from the next column at a what? Lower row. Yes? Yes? 4 Are we done with the transition here? We are, but we need one more equation, which is what? What is the other equation? Is that the summation of the probability of equal to n, comma, n2 equal to what? M, summation over what? N, and summation over what? M has to be equal to what? This is the last equation. Clear? I'm not going to solve. I'll let you do it at home. Clear? I'm going to give you the result. And the result is amazing. Solving the above equations, we get the following. Probability of n1 equal to n, n2 equal to m is equal to 1 minus rho 1 to the n times 1 minus rho 2 to the m. This is equation 5. Where rho 1 is equal to what? Lambda mu1, and rho 2 equal to what? Lambda mu2. Clear? Clear so far? Now, do we agree that this is MM1? Do we agree that this? Okay, forget about this. If this is MM1, what was the distribution? What was the PMF in the system? Did we do this before? What was it? It was like this, if you remember. And it's rho times what? Rho to the, remember geometric? Yes or no? This one? Is this one? This is for the other one. Are you following on now? Yes? And I'm multiplying. What does it mean? What does it mean when I'm multiplying it? This is a joint probability. If I tell you the probability of A equal to the probability of A times the probability of B, what does that tell you about A and B? They're independent. Are you following on that? They are independent. So what do we conclude from here? Let's see. Conclusion. The first one, the number kits in Q1. Notice, by the way, when I say the number of packets in a Q1, what does it mean? Both waiting, being served. The number of packets in a Q1, i.e. N1, and the number of packets Q2, i.e. at any given time. Any given time, same time. Do you understand what same time means? Same time means. What does same time mean? I'm looking at the system at what? Looking at what? One system at one time and another system at a what? At another time. At what? I'm looking at the two systems at the same time. Clear? Are independent. I'm not sure. Did you follow me here or not? Are independent variables. Are independent variables. Clear? Second. What is the second conclusion? Can you tell me conclusion once you see this? The departure process. The departure process from Q1 process from Q1 is also what? With what parameter? With parameter lambda. Yes? which means what? Departure process from Q1 is on. What does that tell you about the inter times? Do you understand, first of all, what is inter-departure times? Times means what? The times between what? Between the departures from Q1. Clear? The inter-departure times are exponential with what parameter? You lost me. Huh? With parameter lambda. You lost me. I can't tell. Okay, let me try again. Let me ask a question. Is the departure times the same as the service times? Let me write the question. The what was the service Q? How was it distributed? The service times of Q1, how was it? Exponentials with what parameter? Mu1. The inter-departure times, which means what? The departures is what? Is exponential, but with a what? With a different parameter being what? Lambda instead of what? Mu. No, you didn't get it. The question is the inter-departure time the same as service? What do you think? Yes or no? And the answer is why? Let's see if you can help me. This is the time. A packet came here. This is an arriving packet. When did he arrive? Arrive to where? Where did he arrive? To the first queue. The queue is empty. Yes? He exited here. Exit from here to here. Can you tell me what is this from here to here? This is what? S1. What is S1? Time? Yes? Or for that packet. Another packet came in here. When will this one start service? This one will start service at this point in time. Why? Because in here, when he came, he found the server to be busy. So he wait until this time. Yes? When will he exit? He will exit. What is this one? What is this one? S2. Clear? Clear? Okay. Another packet came here. What did he find? What did he find? He find the system to be what? Yes? He will start service right away. When will he exit? He will exit. What is this? From here to here. 3. Did you get it? Yes or no? These are the... Can you show me the inter-departure times? Inter-departure times means with what? The between what? Departures. Where is D1? Can you tell me where is D1? As S1. D1 is what? The departure. Yes? Is D1 the same as S? How about D2? Is it the same as S2? D2. Inter-departure between D2 the same as S2? Yes, it is. How about D3? Is it the same as S3? Why? Where is D3? Can you show me where is D3? Is what? Is this one. Whereas S3 is what? Is this one. Did you get it? No, you are struggling here. Did you get it or not? You didn't get it. Let me try. I don't give up easily. Let me try again. Can we concentrate? What is inter-departure in words? Inter-departure times. What it means? It means timed departures. Departures of who? Of the packet from the first queue. Clear? Clear? Okay. A packet came in here. He found the system to be what? Idle. Right away. When did he finish? When did he finish? He finished at what? S1. Okay. Another packet came in here. While this one is still being what? Served. Will he be waiting? Start service. He will start service at this point in time. Yes? When will he finish? S2. Yes? Okay. Now don't look at this yet. Tell me, what is the times? Which means what? Time between what? Departures. What is D1? D1 is the same as... Okay. What is D2? It's the same as S2. Yes or no? Okay. These are the departure. Time between departure is what? S2. Yes? Now, let's look at another. When he came, the Q is what? Idle. He served right away. He will finish here. Yes? Where is the service time? This is the service time. This is the inter-departure time, which is D3, which is the time between the departure. It's between this one and this one. Yes. Is it the same as S3? No, it's not the same as S3. Yes? Yes? You got the point. When will the service times be the same as the inters? When will this, listen to the question, when will the service times be the same departure times? It will be the same if an incoming finds the server to be what? Busy. See this one? He came, not what? Busy. So he starts service right away, and the inter-departure time will not be the same as the service time. When he came, was the server busy? He has to wait, and then what? Being served. So the departure time is the same as what? The service time. You agree? Agree? What did we show from? We show from these equations is that the inter-departure is exponential, but with what parameter? With parameter rather than with parameter what? mu1. Did you get this or not? The inter-departure times was what? Exponential with parameter what? Lambda. Yes? Yes? Following question. Is the inter-departure times from the first queue, is it the same arrival time to the second queue? They are the same. The inter-departure time is the same as the inter-arrival times between what? Sorry, inter-arrival times to Q what? Q2. So what is it? What is the inter-arrival times? Exponential with what parameter? Which means what is the arrival process? To the second Q. Is a Poisson with what parameter? Lambda. Which I can treat the second Q separate from what? Separate Q? Yes or no? And how does it behave? As an MM1. Do you agree with me or not? At an MM1, what is the arrival rate? Lambda rate. Is this an MM1? That is we already know that what? We already know. BMF of this is this, which is what? 1 minus rho 2 times what? Rho 2 to the what? M. Where rho 2 is what? Lambda. Did you get it or not? Very powerful theorem. This is called, by the way, Burke theorem. You will study it more in detail in EE, assuming you take this class 5 and EE 550. But I just wanted to show you the highlights. What it tells you if you do, remember, by the way, what kind of a network are we dealing with? We are dealing with forward network, which means what? The packets are not allowed to visit a queue more than once. Clear? Yes or no? What does it tell you? What does this theorem tell you? That you can treat each packet independent of what? Independent of the other. What is an MM1? Yes or no? Okay. So remember, when if the departure times of is exponential, parameter lambda, that means the inter arrival times to Q2 is also what? Exponential with what? Parameter land, which means what? The arrival process. The arrival process of the arrival. Q2 is what? Boson. Clear? Clear? You can help me. Example. Let's assume I have the following. I'll explain to you what P is in just. Yes. Question. Word. There's a feed forward. There's no feedback. In other words, the packets are not allowed to what? Are not visit the queue more than once. Clear? Okay. Let's understand what do we have here. The packet externally at what rate? At a rate of lambda 1 Poisson. Yes? Okay. It gets served with a probability of P. It will what? Join this queue. With a probability minus P, it will join what? This queue. Yes or no? Okay. Let's see. Find the probability of N1 equal to N2 equal to what? N2, N3 equal to what? Let me use different symbols here. N1 equal to what? N, what? M, N3 equal to what? K. What is this? What do I call this? What do I call this? That's the joint PMF. The joint PMF. Clear? Okay. Also find E of what? N, which is E of N is the average number of what? Packets in the system. Clear? You can help me. Okay. And what did Burke tell us? Is this word? What did he tell us? He tell us we can treat each what? Each packet independently. Okay. Tell me. What is the probability that N1 equal to N equal to what? M, N3 equal to what? K. What is it? The probability of what? N1 equal to N times the probability to equal to what? M times the probability that N equal to what? K. Clear? Now listen to me. Let's start with this one. Is this MM1? It's MM1. Do we know the probability? What is it? 1 minus times what? Rho 1 to the what? N. Do we agree? 1 is what? What is rho 1? Lambda. Sorry, divide by what? Mu1. Do you agree? Do you agree? Okay. Now, what? Now, the departure process. The departure process, what did we prove? It's also what? Poisson with what parameter? Understand? The departure process. The departure process is what? Poisson. Yes? Get when you split Poisson traffic into what? Into two paths. Do you still each one also be Poisson? But with what parameter? P times what? Lambda. And this one will be what? 1 minus P lambda. Did you get this or not? So what is it? Give it to me, the next one. What is the next? This one. What is this? 1 minus rho 2 times what? Rho 2 to the 1. Yes? Where, what is rho 2? Let's see if you can tell me what is rho 2. Row 2, which is what? The server utilization of this server. What is it? Still waiting. Times what? Lambda over what? This is not row. This is P. This P. Did you get it? Yes or no? Yes or no? Help me. Is this Poisson? That's external traffic. Is this a Poisson? Poisson. What do you get when you aggregate two independent Poisson? Do you get Poisson also? The splitting of Poisson is what? Poisson. Aggregate of Poisson is also what? It's also Poisson. As long, of course, they are independent. And they are independent. This externally, whereas this one is internally. Clear? What is this one? 1 minus row 3. Yes or no? At times what? Row to the m. Now tell me what is row 3? To the what? Sorry, to the k. I'm sorry, to the k. K. Can you tell me what is row? What is row 3? It's 1 minus e times what? Lambda 1. This is lambda 1. I'm sorry. This lambda 1 also. 1 minus p lambda 1 plus lambda what? Divided by what? Mu 3. You lost
me. The time is 3 o'clock.
You lost me here. Is this external traffic? Is this Poisson? The Poisson. At what rate? Here, the Poisson at what rate? What is the departure rate? Which is the same as the arrival rate. What is it? Lambda. But it's only 1 minus p. So I minus p times what? Lambda 1, yes or no? And then I need to add to it what? Remember one more time. Aggregate. If I tell you, listen to me. If I tell you z equal to what? They are independent. Each one of them is what? Poisson. This one in 503. No matter who the professor is. You must have had it in 503. If x is a Poisson and they are independent, and let's assume has a parameter of what? Lambda 1. And this one has a parameter of what? Lambda 2. Be Poisson. It will be Poisson. With what parameter? Lambda 1 plus lambda 2. Is this Poisson? This is Poisson. Is this Poisson? Why is this one Poisson? This one is Poisson because I just proved to you that the departure process from here is what? A Poisson. The price for the next one is also Poisson. Yes? So it becomes what? What is the departure rate from this one? Not the service rate, the departure rate. The departure rate is what? Is lambda. You didn't get it. You are struggling here really badly today. Can we concentrate a little bit? Did you get it or not? What is the arrival process here? Is it with what rate? Lambda 1. What did I show you a moment ago? The inter-departure time. The time between departures is what? Exponential. With lambda. Yes? What does that mean? It means the departure process with what rate? Lambda. Now, the departure process is the same as what? Arriving process to these two. Yes or no? So this is how they are going to split. The Poisson traffic are going to split. P of it will come in here, which rate here? P lambda 1. What is the arrival rate here? 1 minus P lambda 1. Each one of them is Poisson. Each one of them is Poisson. In addition, external traffic, which is also what? Poisson. What do you get when you aggregate Poissons? Poisson. But at a what rate? The sum of the rates, which is this. 1 minus P lambda 1 plus what? Or what? Mu. Clear? Clear? Okay. 1. Let's see if you remember the equation. I doubt it, but let's see. Equation for E of N1. What is E of N1? E of N1 is the number of what? Average number of packets, both weight served. Yes? What is it? Rho 1 over what? Rho 1. Agree? Okay. What is E of N2? It's the same thing over what? What? 3. Rho 3 divided by what? 1 minus rho 3. What is E of N? E of N is what? Clear? Is the average number, so? Yes or no? Now, for the tricky one. Let's see if you can help me with this. E of T. Now, first of all, let's understand what E of T is. What is E of T? E of T is the average time spent by a packet, average time spent by a packet in the system. From the time he gets in, he gets out. Did you understand what I just said or not? Okay. Now notice, by the way, packets are coming here. And some of the packets are coming here. Notice the packets in here are going to what? To leave earlier than the packets that are coming in here. Do you agree? Why? Because in here, you need to go through how many queues? 2 queues, not 3 queues. 2 queues. This one, yes? Whereas this one is only going to go through this. But I'm calculating the average. Yes? What do you do? What does Little's theorem tells me? What does Little's theorem tells me in general? Little's theorem. It tells me E of N is what? Times what? E of T. Do we agree? Do we agree? Now, E of N. Did we calculate E of N? This E of N. Yes? Can you get me E of T? How? What is E of T? It's N divided by what? Lambda. Lambda 1 plus what? Lambda 2. I'm sorry, lambda 3. Did you get it or not? Yes or no? I will prove to you that you didn't get it. Let's see if you can tell. Is this true? Try this, just answer me. Is this true? Is this true? E of N? E of N, I said what? It's E of N1 plus E of N2 plus what? E of N3. Is this true? No, this is not true. Are you following that? This is not true. When you apply theorem on the overall system, you as if what? All the internal, in other words, this is what we, if you are applying Little's theorem, look what we are looking at. What are the external arrivals? The lambda 1 and the what? Lambda. All of these are internal. These are internal system. So when you apply Little's theorem, it's like you are looking at what? The whole thing at just what? And you consider only the what? The external arrivals. What are the external arrivals? Are lambda 1 and what? Lambda 3. Clear? I need to make it clear. T1. Can you tell me what is E of T1? What is E of T1 separately? E1 over what? Mu1 minus what? Lambda 1. Do we agree? Agree? What is E of T2? It's what? 1 over mu2 minus P lambda 1. Do you agree? What is E3? Mu3 minus 1 minus P lambda 1 plus what? Close the bracket. Do you agree? If you add this, would you get this? Plus this, would you get this? You will not get this. You follow me or not? Which one is the correct one? This one or this one? And that will definitely be in the midterm. No question about it. No question about it. You said or not. when you calculate, when you do a network of queues, and when you are looking at what? Applying Little's theorem, we take the what? The external arrivals into consideration. The internals, by the way, they might be queues, like I will show in just a second. Clear? Clear? Is this one correct? E of n equal to what? E of n1 plus E of n2 plus E of n3. Is this correct? Is the expected number? Yes, that is it. Clear? Okay, so just let me write this. This does not equal E of T1 plus what? E of T2 plus E of T3. Clear? Clear? Okay, now. After Burke came up with this theorem, came another name is Jackson's. Let's see if you can help me understand what, for those of you, the 503 with Professor Sonis. How many of you took it with Professor Sonis? None of you? Did he? Huh? Did he cover this or not? Cannot hear you. Okay. No, don't worry about the name, but did he choose? Let's see what he did. He said, okay, let's assume the queues is no longer what? Feedward. In other words, he assumes that if there is a feedback. Feedback means what? Means allowed to what? To visit. A packet is allowed to visit a queue once. Let's take a scenario so that you understand how would that happen. I'm a queue. I'm sending the packet. One packet was received in error. The system that is used is ARQ. Remember ARQ? What is ARQ stand for? Repeat request, where the receiver is going to tell the sender, send it again. When I say send it again, it means the packet that I send will go back to the what? To the queue to be sent again. It will go back to the queue to be sent again. Clear? Clear? Or let's see if you can help me. I have a buffer. These are the external. Yes? Now I'm going to designate the external by GAM rather than land because I want to emphasize one point here. Did you get it? Is what? Poisson arrivals. What? External. Poisson or what? External. Clear? Okay. This is the server. Will leave the system with a probability of what? P. It will what? Rejoin this is with a probability of what? 1 minus P. Did you get my point or not? Is there a feedback? Is there a feedback? This is feedback. Clear? Now, what? By the way, I'm not going to show you the proof. I'm just going to show you the conclusion of this here. He says, Poisson, yes? By the way, what is the aggregate? What is the aggregate? Is this plus this? This internal, this is agree? He said the following. The incoming traffic to this queue are what? Poisson. Why? First of all, what is the property of the Poisson traffic? Traffic means what? Means that the traffic in any instant of time does not depend on what? On the previous times. Yes? Cannot hear you. Listen to this. Assume P is a small. What does it mean? It means most of the traffic is coming back. Agree? Is coming back. If the external arrival rate is a small, what you see in here, what kind of pattern you see? For a short period of time, you will get arrivals, followed by what? Followed by a burst of what? A burst of, you follow me or not? The pattern is going to what? Repeat itself or not? Which means if you know the pattern in one interval, you can get an idea in the what? In the next interval. Did you understand that or not? External are coming what? At a low rate. What? But if P is small, if P is small means what? Most of the traffic is coming back. So you will see small external arrival rate followed by what? Bursts of what? Packets being returned, and it will repeat itself, which means what? It means that the property of the Poisson process is no longer what? Is no longer valid. Are you following me or not? So the incoming, again, the incoming traffic is no longer Poisson. Clear? Poisson. But he showed, which I'm not going to go to the proof is too long, but he showed still treat this one, we can still treat this one as a what? One. Are you following me or not? Clear? But he still showed, that the probability of n equal to n, what is the probability of n equal to n means? EMF of what? The number of packets in the system, both waiting and being what? Served out that the probability of n equal to n is still what? 1 minus times what? Rho to the n. Did you get this or not? Where rho was equal to what? Let's see if you can tell me what rho is equal to. Rho, gamma, yes? Okay, let me explain to you one thing here. Aggregate traffic. The aggregated traffic, I'm going to call it what? Lambda. Yes or no? He showed gamma plus what? 1 minus P times what? Lambda. Why? I need you to understand why is lambda. He showed that the departure process, from this Q, the departure process from this Q, lambda. Are you following me or not? It's lambda. Clear? Which means what? It means this one and this one is what? 1 minus P lambda. Clear? So he saw that this lambda times is P lambda over what? Over mu. Clear? No response. Clear? Let me ask, sure if you got my point. What is the throughput of this system? What is the throughput? What is the throughput of this system? Still waiting. Repeat that again. Who's saying? I'm not sure who's. Yeah, P, very good. P lambda. This P is not the rho. It's not the probability. This is the throughput. These are coming in. Yes or no? Yes or no? What is E of n? Let's see if you can tell me what is E of n. Still waiting. What is the average of this one? Is this geometric, by the way? What is E of n? E of n is rho over what? 1 minus rho. Remember, the rho. Yes? Cannot hear you. Okay, now what is this? Still little theorem. What do I do? Is this to write two equations? E of t is equal to what? Which one is correct? Sorry. E of n over lambda. E of n. Which one is correct? This one. Are you following me or not? This one. All of the stuff. It's already included. Are you following me or not? Included in the definition of rho. Clear? So. Over what? Clear? What is the relationship between lambda and gamma? Relationship between lambda and gamma? What is lambda equal to? What is equal to? Gamma plus 1 minus P times what? Lambda. Which means, can I get this one to this side? So what do I have? Lambda. Sorry, P. Help me. The lambda will cancel. Yes? So it's what? Lambda equal gamma over what? P. Clear? Clear? Then which one is bigger? Lambda or gamma? Gamma is equation. Lambda equal to gamma over what? Over P. Which one is bigger? Of course lambda. Are you following me or not? Yes or no? By how much is bigger? In other words, when I say if lambda is, let's assume lambda is equal to what? Yes? Where is this to? Where did it come from? This is the average number of times the packet will what? Visit the queue. Did you get it or not? Did you get it or not? Because every time this one is coming back, every time this one is coming back, it will contribute to the what? To the overall gap. Or not? If this one is, listen to me, if this one is not coming back, what is the lambda? This one is not coming back. In other words, if P is what? 1. This one is not coming back. What is the lambda? Lambda is equal to gamma. Yes? Why? Because the average number of visits is 1. But if this one keep what? Keep coming back, the lambda will become what? Higher than gamma. Are you following me or not? On the average, depends on average, how many times you are what? You are going to come and visit the queue. Clear? Clear? What is that? What is that average? Look at the equation and tell me what is that average. 1 over P. Excellent. So the average number of times a packet. You do understand this times we are not talking about what? Time in second. Average number of times means what? It means average number of times. Yes? It's not in second. In other words, how many? Clear? Average number of times a packet visits the queue is what? 1 over P. Is this more than 1 or less than 1? More than 1. By the way, could it be less than? How? You have to go through a what? You have to go through the system how many times? 1 time. Do you follow me or not? This one is greater than 1. So what is the lambda? One more time. Lambda is what? Gamma times what? Number of times the packets will visit the queue. Clear? Clear? See if you can help me. Suppose I have this. Change this one into what? I'm sorry. Change it to what? God. Can you help me? First of all, do you understand what this means? The packets arriving, yes, are being served by the first router or the first server with a probability of 1 mile will go what? Exit the system, they will go somewhere else. Yes? With a probability of P, the queue. Yes? Sorry. Queue, and those will what? Will return to this side. Yes? With what probability, by the way, here? With probability of 1. All of them will what? Will exit the system. Yes? Okay.
Hello, Professor. This is a 5-minute warning.
Thank you. Yes? Okay, what is row 1? Okay, let's see what do we have here. What is of these? This is lambda 1. Yes? Cannot hear you. Okay. What is the departure rate here? Here. Lambda 1. What is this? P lambda 1. What is this? P lambda 1. Huh? I messed up?
Yes, 1 minus 0. This is not the we're treating these two as like 2m and 1, right? So is that the 1 minus rho to the n multiplied by 1?
Oh, jeez. What am I doing here? Sorry. 1 minus row 1. I'm sorry. Row 1 to the what? I'm sorry. 1 minus row 2 times what? Row 2 to the what? M. I was writing there. Clear? Okay. Now help me. Help me. What is this? Lambda 1. What is the departure here? Lambda 1. What is this one? 1 minus P lambda 1. This one. P lambda 1. Yes? What is this one? P? Yes? Yes? Okay. Which means what? What is lambda 1 equal to? Plus P lambda 1. Yes? That's the aggregate to it. In other words, this whole thing is equal to what? I already wrote. Yes? Which means what? What is lambda 1? Gamma 1 minus P. This is P, not rho. This P, not rho. Okay, what is rho 1? What is rho 1? Rho is lambda 1 over what? Mu 1. Yes? What is row 2? What is row 2? It's P lambda 1 divided by what? This is P. It's not what? Not what? Not rho. This is P. Clear? Clear? What is the throughput of this system? What is the throughput of this system? 1 minus P times what? Lambda 1. Did you get this or not? Okay. If I want to calculate E of T, which is the total time spent in the system, what do I need to find? E of N, and what do I divide it by? Are you following me or not? Gamma. Do not divide it by lambda. All of these are internal. Clear? The external traffic is just clear so far. Yes or no? Okay, good. Now, next time, what we are going to make sure to bring this one with you next time, which is the new set of traffic flows. We are going to be looking at networks like this. You see this? We have external traffic flows. Are you following me or not? External traffic, internal flows. Clear? The gammas are what? External flows, and we need to figure out how we calculate the average, what? The average time spent in the system. No response. Clear? Yes or no? Now, bring this chart with you, please, next time. Don't forget about it. Okay. I think I ran out. I will see you next time. You have something due today? Homework due. Okay. Do not, by the way, how many of the discussion session yesterday? Did he give you some examples? Okay. Now for the next session, I will give him to present to you examples on this, on the MG1, on the prior, so forth. Do not miss a discussion session. Discussion sessions are extremely important. Clear?
This concludes the 555 with Dr. Zahid, January 13.